direct thrust control of linear induction machines for metro applications. So the detail our respectable speaker, Dr. Abdul Khalik Junejo Saab from Department of Electrical Engineering, Qaidewan University of Engineering Science and Technology, Nawabshah, Sindh, and he is assistant professor there. So he will introduce a little about himself, and then he will start on this topic. Over to you, sir, please.
So, Assalamu alaikum. Hi guys. So, good afternoon. So, today, first of all, I want to introduce myself. I am Dr. Abdul Khalik Junaid. I did my PhD from Hast University, China. So, now I am serving as Habib already said that in Department of Electrical Engineering, Kaidoam University of Engineering Science and Technology, Nawabshah. I am also peer reviewer of the IEEE Transaction Series journals, and I also publish more than 15 ACI journals in the reputed journals just like IEEE Transaction in Power Electronics and IEEE Transaction in Vehicular Technology and IEEE Transaction in IAS. So this is a little introduction about me. So today our webinar on slide mode control based direct thrust control for the linear induction machine for metro or subway application. So it means that we will apply the slide mode control on the induction machine, but this machine should be a linear and which can be used as a metro or subway. So first of all, I want to go for the outlines of my presentation here. First would be the introduction, then operation principle of LIM and the proposed slide mode control for the system. And this system is validated or the proposed SMSC, which is already applied on LIM, and it is validated by experimental results. And then we would conclude this lecture. So introduction, the linear electric machines gained the industry after the 1960, although it has been invented in early 19th century because the need of power electron for the motion control. LIM derived from the rotating induction machine, which can be achieved direct linear motion without any motion transformation gearbox from the rotating or linear. Recently, LIMs have been paid more attention from both academia and industry for their advantages of direct drive, greater acceleration and deceleration, and compact volume. Next, LIM has served as an excellent option for the urban transport transaction traction drive system due to its superior ability to generate direct forward thrust without using mechanical transmission. Because you know that we are talking about the linear electric machine, so that's why we can say that it is a supreme ability to generate direct forward thrust without any mechanical transmission. So till now, there have been over 20 commercial linear metro lines in worldwide, including Vancouver Light Train, which is in Canada, and Candy Line in America, Beijing Airport Transit Rapid Line in China, and HST in the Tubo in line. So Guangzhou Subway, Line 4, and so on. So it means more than 20 commercial line already built in the world for the linear induction machine.
Excuse me, sir,
Yes.
I am just interrupting you. You are on slide one or which slide? Because slide one is visible. Just
So
your title.
no, I am on slide number 4. So it is
Yes, it is stuck,
yes.
I think, so not visible. Only on first. Can you please close it and then again open it? Maybe the issue.
So
Yeah, yeah.
now
No is okay. No is okay. No is okay. Yes.
now is
Please
okay.
continue.
It
Yes,
is
yes,
okay. It is okay, I
yes,
think.
yes.
Okay, so as a picture, small picture is there, and we can see there is the primary and secondary, because actually in the electrical machine we have two means mechanical conversion system. One is the electromagnetic and the mechanical. For example, we have two parts. One is a rotor, another is stator. For the rotary induction machine, we know that in rotary induction machine, one is the stator, another is rotor. When we give the electric current or voltage to the stator, and due to the mutual induction, the rotor will rotate over there according to the magnetic field. But here we can see that there is a primary and there is a secondary. So there is a secondary with the rail. So that is why we say that this is the linear metro. For high performance control techniques for the LIM, linear induction machine, two control methods are used such as field oriented control method and direct thrust control method, DTC, which is very well known. There are two methods, one is the field oriented and direct thrust. And everyone know about the vector control, which is a field oriented control method for the electric machine. Either machines are linear or rotary machine. So we can apply a different control strategy to control the speed and thrust and current and voltage of the rotary and linear induction machines. So now here we choose the direct thrust control method, which is known as DTC. So DTC strategy has more advantage compared with the field oriented control, such as less dependency on the machine parameters, high efficiency, and does not require the current regulation loop or coordinate transformation. So as if we apply FOC, so we need a current loop also, and also we need some coordinate transformation such as Parks and Killer-X transformation. But when we choose the DTC, we don't have a need of the current loop, and also we don't have need of a coordinate transformation. So in this presentation, we choose the method as a DTC for the slide mode control. Application is linear induction machine. So the conventional DTC for LIM has some drawbacks such as higher thrust ripple, higher primary flux linkage ripple, and variable switching frequency. These are the drawbacks of the conventional DTC. Now several modifications are used to reduce the primary flux linkage and thrust ripple and achieve constant switching frequency. In this presentation, the switching table is replaced by the space vector modulation for the voltage vector selection to achieve a constant switching frequency. As regards the speed loop control, it's common to use PI controller for all research, but the behavior of PI controller in the flexibility to load variation is much poor. So as everyone know, for the speed control, because when we talk about the drive system, one drive system may be a PMSM drive system for a linear induction machine, drive system for the induction machine, drive system for the any other motor. So we need some controllers to control the speed, to control the voltage, to control the current. So for controlling, we use PI controllers, but PI controllers has some disadvantages. So here we talking about the speed control. So speed control under the PI controller, it has some limitation whenever a load is applied on the machine. For example, when a motor which is used for the electric vehicle, for example, any height will come. So this controller has some disadvantage whenever load is applied. On the other hand, advanced control method, they needs adjustment and optimization in the control procedures, such as makes it difficult for the control system based on to them to precise both hardware and software. For example, we are talking about optimization. In optimization control, we need high computational power, because we know that we are using more than 100 or 200 or 300 iteration over there. So we need a high computational power, so that it is very difficult. So the slide mode control is applied in the linear induction machine control system because of its robustness, easy to realize, and ability to load variation. So that's why today we will talk about the slide mode control for the LIM. Therefore, here I choose one type of slide mode control, which is known as terminal reaching law based slide mode control under direct thruster DTC is proposed here for the induction machine drive system. So now that was the introduction. Now we are talking about the operation principle of a linear induction machine. So how linear induction machine would be there? The model of LIM is built in stationary reference frame alpha beta with the help of equivalent circuits shown in figure. As we know that every machine has an equivalent circuit. So this circuit is for the linear induction machine, and we can model it with a stationary reference frame which is alpha beta coordination, because we have to convert from three phase to two phase, so that we are using Parkes and Clark's transformation for the any machine. So the dynamic mathematical model of LIM can be constructed by using the synchronous reference frame. The description of voltage, flux linkage and thrust are given here. So these are the equation in the D and Q form of the linear induction machine. This is the mathematical model for the LIM. So these are the equation for the LIM. The electromagnetic developed thrust can be expressed in this equation as F equal to 3 pi divided by 2 pi. Then there is a flux linkage and the IQ current. Then there is a minus of the flux linkage with the current in the D and Q. And this is the motion equation for the LIM, which is given here. Fe equal to Fl and plus mv vr, and there is a disturbance term is which is used there. Whenever we talk about any machine, it has external disturbances and internal disturbances. So external disturbances can be is a resistance variation, parameter mismatch, and external disturbance just like a load applied to the machine. So propose slide mode control for the LIM. So here the principle of the DTC. First we have to talk about the DTC, how DTC can work. There are 8 voltage vectors resulting from the combination of switching state for each switching device. This figure shows that the 6 active voltage vector from U1 to U6, where 2 voltage vectors are 0, U0 and U7. As we know that, for example, we have a machine. If machine is controlled by using different controllers, so I want to show here one diagram, then we will return back our origin slide. So in this machine there is a LIM, there is an inverter, voltage source inverter is here, there is a space vector pulse width modulation, and there is a transformation from the DQ to the alpha beta, and there is a PI regulators or PI controllers for the voltage and for the thrust. This is thrust and this is the flux, and this is the speed loop which can be senses or which can be taken feedback from this by using some sensors, and we take here and we compare both signal of speed, then we apply the SMAC instead of PI controller. So this is the whole control strategy of any machine. For example, if there is a PMSM, if there is a DC motor, if there is a BLDC, if there is a induction machine, rotary induction machine or linear induction machine, the block diagram would be the same, only this machine can be changed over there. So inverter, we know that inverter we need the DC supply, and it will go here and change DC into the AC by using the voltage source inverter, because our machine is linear induction machine. So this machine is AC machine. If there is a DC machine, so there is no need of this inverter. And there is a space vector pulse width modulation which can generate pulses for the inverter. We know that how inverter work on the different pulse width modulation techniques, just like SPWM, SVPWM or SPWM. And nowadays there is a modern technique is used here which is known as a MPC, model predictive control. So model predictive control can be used here to reduce the thrust ripple. So we are going in the previous slide to understand the direct thrust control. So here is a just like a switching, just like a space vector pulse width modulation. So whenever we got a best vector, then we will choose the best vector for the modulation technique. So the neglecting the primary resistance and primary voltage equation can be rewritten in the vector representation form as follows. And it can be noticed from the above previous equation. From the previous equation, the primary flux can be directly controlled by controlling the primary voltage. It means whenever we control the voltage, it means we are controlling this flux because it has a direct relation. So that so the electromagnetic developed thrust can be calculated from another form by using following equation. For example, this equation according to the thrust equation by assuming the secondary flux to be constant and under constant primary flux, the rate of increase and decrease of thrust is proportional to the to flux angle. This is the flux angle. Now we can say that the rate of increase and decrease thrust, because whenever you control the speed, after the speed there is some regulator. You can use PI regulator, you can use the fuzzy logic control, you can use neural network, you can use slide mode control. After the slide mode control, you directly take as a thrust, or you directly take as the IQ reference current for the rotary induction machine. So whenever we talk about the rotary induction machine, it means it would be the just like a torque, just like a IQ. And for the linear induction machine, it is a thrust. So after the slide mode control, after the PI regulator in the speed loop, we directly take as a thrust. So here it can be noted that the procedure increase or decrease of thrust rate achieved by selecting a switching voltage vector that increase or decrease the flux according to this angle. So according to this angle, we can see that, for example, this angle, this is the reference. For example, this angle, whenever this angle would be greater, so we can take a different flux rate on this relation between primary and secondary flux vector in alpha beta frame or stationary reference frame. So therefore, by choosing the appropriate primary voltage vector, both thrust and primary flux can be controlled simultaneously. The choice of optimum voltage vector to achieve the required value of flux and thrust is introduced in this figure. Choosing the optimum voltage vector based on required value of the flux and thrust. So this is the again basic block diagram for the linear induction machine. For example, it has three loops. One loop for the speed loop, another loop for the flux loop, another loop for the thrust loop. For example, if we want to control the speed, so we should have to design our controller for the speed loop. So this is the speed loop, this is the reference speed. For example, this metro, we want to operate the metro line or subway or any train or electric vehicle on the 1000 RPM. So we give reference speed over here. And we can calculate what would be the feedback, means output speed is the same 1000 or somehow smaller than 1000. Then we compare both speed over here, and there after comparison there would be the error. This error can be regulated by any controller, for fuzzy control, for neural network control, for slide mode control, for the PI control. So actually we are talking about here slide mode control, because which is insensitive of the parameter variation, and it is a very robust against the load disturbance, and which has a superior property than the PI controller. So here we will design here slide mode control for the speed loop, and for the thrust loop and for the flux loop, the PI regulator would be the remain same as a conventional PI controllers. If we want to design slide mode control here, we can design. If we design slide mode control here, it can be designed. So it is depends on the performance equation over here. So the design slide mode control, actually for the designing of slide mode control, we have two subsystems. For example, one is the slide mode surface, another is the reaching law or control law. So in reaching law or control law, we design such an equation if state is any place. For example, whenever machine is start, when machine is start, it means it is start from 0 to the rated value, whatever you give the reference to the machine. So whenever you give the 5000 rpm or 4000 rpm or 1000 rpm, it is the reference, but machine state or machine initial position would be the 0. So the work of the control law or reaching law is there to take this reference value on the rated value. So we have to design one equation for the control law, another equation for the slide mode surface, which can be used, for example, sliding state which come from any state and come on the rated value. Now we want to make error equal to 0. So how we have to make error equal to 0? But it cannot be 0, but we want to try to minimize it because we want to take a very strong control. So we have to design slide mode surface over there. One equation for slide mode surface, one equation for the control law. So here, as we discuss about the speed equation, so here the control procedure to find the control law so that the LIM, linear induction machine speed, can track the desired reference based on the LIM mechanical equation. So here one equation, speed equation is here for the machine. So where M and D are the total mass and viscous coefficient of LIM respectively, with B n equal to this, A n equal to this are the value of parameter in the nominal condition. If the external disturbance occur in mechanical equation can be modified as here, because whenever external disturbance means load disturbance given to the machine, first equation was this would be the same, this would be the same, and now we are introducing disturbance or total uncertainty which may contain the external disturbance and internal disturbance to the machine. So how we have to design a slide mode control for the speed loop of LIM? First, the speed error is taken as the state variable of LIM and its derivative is denoted by E dot. Because we know that I again goes to the here in the block diagram. For example, in this block diagram, we can see that one speed or feedback speed which come from the machine, another speed which is reference speed given to the machine. When we have to compare these both speeds, we take the output speed as an error. So error would be here. So that we have designed slide mode control for the for example, slide mode control is the function of error. So error would be here, and this slide mode control regulate this error. So how we have to design? So we can design here equal to reference speed minus actual speed. Now we are taking the derivative of this error. It would be the x1 dot or first derivative, then it would be this is the reference speed and this is the actual speed. So this is the reference speed dot and actual speed dot. The slide mode surface and terminal reaching log can be written as, because I already told you that for the slide mode control for any application, it can be used in the electric drive system, it can be used in the machines, it can be used in the robotics, it can be used in the renewable energies, it can be used in power electrons. So slide mode control can be used in many applications over there. So for the slide mode control design, you have to design two things. One is the slide mode surface, another is the reaching law. So here slide mode surface is taken as a this speed means this reference, this slide mode surface S equal to E dot plus, this is the constant, epsilon is the constant, and multiply with the E is the error. Now this is the control law, reaching law. This control law or reaching law is the responsible to take the state here. State is what? It is the error. So now this equation is responsible to take this error from any position to the to design slide mode surface or rated value which you want to give to the machine. So this slide mode this slide mode surface is responsible for state to stay on the rated value or at one line. By adding the previous equation, the thrust reference of the slide mode speed control can be obtained by S. Now here we have a error equation and we have a slide mode reaching law and slide mode surface. By adding previous equation, these are the previous equation. In this previous equation, when we use this error and we use all equation or all compute equation in this form, you can take the thrust reference by using slide mode control over. This is the final equation when you will add add the previous equation in these both two equations. So you can take this equation after adding all equation in the previous equation, then you can find the FE. FE is the thrust reference. So now here, so for the control system, it is important to design. It is important to analyze it by using stability functions. For the slide mode control, we have a Lepnow theorem to check what we have designed, it is stable or not stable. So according to the Lepnow theorem, the reaching condition must be satisfied. The reaching condition for the slide mode control should be S is the slide mode surface, S dot is the control law. Means surface and control law, when we multiply both, it should be less or equal to 0. So can be verified so that design controller is asymptotically stable, which can guarantee the system reach to the slide mode surface. For example, Lepnow equation is here. This equation would be just like this. Now we putting previous equation for the control law and surface, and we solve it by using mathematics equation and mathematics inequality. Finally, we got this equation. This equation contains negative values. It means that whenever all negative value come in the final step of the equation, we can say that these are less or equal to 0. So the reaching condition is a satisfied on design control of slide mode control system for the LIM. After that, we built one experimental setup to to validate our proposed method for the linear induction machine. For example, here is the linear induction machine which is shown here. Now we can see here there is a one rotor, there is a one stator, but stator is cut it here. So whenever we make some arc, just like arc stator, when we make arc stator, it is not no more rotating because we make a prototype. So for example, we don't have much space in the laboratory to make one whole linear, but we can make a arc. This arc induction machine is a resemble to the linear induction machine, and we apply our proposed control strategy on this practical prototype, and we can check the design control method, and we can check the and we validate our design control method. So the parameters of this experimental setup are used to apply the proposed control method. For example, we have there is a DC source because inverter need a DC. So this is a DC source. In DC source there is a rectifier which give a DC link voltage, and there is an inverter which convert this DC voltage into the AC voltage, and it is given to this machine by using some microprocessor control over there. And there is a regulator. This regulator show that how we regulate this VDC, means DC voltage for the inverter. And there is a one PMSM machine is coupled with on the same shot. This PMSM shows that this is the control machine, this is the load machine. So on this PMSM we give some current in anti to the induction machine, which produce anti torque on the same shaft, and we assume that this is the load on the machine. So these are the experimental parameters for the LIM are listed in this table. The rated thrust, which is shown here, the value would be 280 Newton, and rated power is shown here. This is the 3 kilowatt, and rated speed is 11 meter per second, and the rated voltage is given here 180, and the rated current is given 22 ampere, and the pole pitch is given here. Primary length of the machine is given, secondary resistance of the machine is given, secondary leakage inductance are given here, and the primary leakage inductance is given here, primary resistance also given in this table. These all parameters for the LIM machine or linear induction machine. So now here we took some cases to validate the proposed method. For example, here variable speed under constant thrust load. Now you see here thrust load is 120 Newton, which is applied on the machine at the reference speed from 0 to 3 millisecond, and again increase from 5 to 5 millisecond at the time of 2 second to the 4 second respectively. For example, this machine start from here from 0, it goes to the 3.5, again increase because we want to check the robustness of the speed under different speeds. So here this speed is the 3.5. Now again this speed change from 3.5 to the 5.5, and at the 2 second to the 4 second, then this speed remain constant. What we have analyzed here, because one is the conventional, red show the conventional DTC which is on PI control method. So another is ERL DTC, another is a TRL DTC. For example, these two DTC are based on slide mode control. So now this CDTC means conventional DTC, which is on just like for the PI. For example, I want to again show you block diagram here. So here is the block diagram. For example, the conventional DTC, here is a PI controller. For the proposed method, there is a TRL SMC. Another method which is compare, which is conventional ERL SMC. So we compare three methods on the same machine with the conventional DTC means our ERL SMC is better than the conventional SMC, which is based on the PI regulator, and TRL SMSC is superior than the ERL conventional SMSC. So here analysis is given. So here we can see that our TRL DTC is superior than this red and this blue. So red is on conventional DTC and blue is on ERL DTC. It is also slide mode control. So it can be visualized clearly here that the slide mode control is better than the PI control system. So it can be seen from picture that the proposed method is a faster response and good tracking than those of conventional DTC and ERL DTC. Again we can see the thrust, that is a speed. Now we want to check the current or thrust. So here thrust directly proportional with the current. So thrust load is 120 Newton. The reference speed changes from 0 to 3.5 meter per second, and again increase up to 5.5 meter per second at the time of 2 second to the 4 second respectively. Now we can easily see that the actual flux linkage and thrust tracks the reference and the flux linkage with the acceptable very small variation during the speed change, and thrust is a big value due to the load connected. Now TRL DTC has the small ripple. We can see that TRL DTC has a small ripple as compared to CDTC and ERL DTC. So this response for flux, this response for the thrust. So now we want to check the current. What would be the input current to the machine whenever speed changes with the load? So load already connected with machine. For example, this machine is used for the linear metro or subway. It means all people are sitting in the metro, and now metro can start from one speed to another speed. So at that means practical example or application, we want to see the responses on the different controllers. So here again we can see the input current under the TRL DTC or slide mode control is better than the PI controller. It can be observed very easily. You observe the three phase current under the slide mode has a lower current than the both methods other just PI and ERL. So another case we built here. First case was load is constant. We change the speed. Now load means load would be the change, speed would be the constant. For example, for the some period, the people sitting in the metro are 100. Now the number of people is changing, but the speed should remain constant. Then what would be the behavior of the machine on this? So it so here initially 100 Newton load is applied to the LIM, and then load is increased to the 200 Newton at the time of 4 seconds under the speed of 5 millisecond. So we can see here the speed reference is the same here, 5 millimeter per second, but the load is changing at this point. Initially the load was 100 Newton meter. After some time the load is at 200 Newton, means double. So we increase 100 times load on this position, and we can check that the slide mode control response is more better than the PI regulator control method. And also we can say that when load is applied to the machine as a double, also it can be checked here the response is based under the slide mode control than the PI regulator. So here, so we can check, we can easily check here. Now we can check the thrust. Whenever load is 100 Newton meter, after some time load is increased as 100 times. So we initially we can see that there is the response with the 100 Newton. Again when load is increased at this point, this is the starting point of the machine. This is the 100 Newton meter. After this time the load is increased. So here we can say that the thrust ripple is a similar under the slide mode control than the conventional DTC or PI regulator. So now again three phase current can be checked here. So we can check the three phase current. It can be seen from this picture that the input phase A current is better than the ERL DTC and CDTC respectively. The little fluctuation has been seen which are due to the end effect. So maybe in the next time we will talk about the construction of the linear induction machine, how we can construct. This is all about the control, how we have to control the speed of the linear induction machine. So it is the control side, not design side. And next time when we talk about the design side, then we will surely talk about the end effects of the linear induction machine. So now here conclusion. So in this talk or in this presentation, we can say that the terminal reaching law based slide mode control with the direct thrust scheme has firstly proposed for AIM. A is the arc induction machine drive system, and we already demonstrated and validated by using experimental analysis and numerical analysis. So here TRL DTC is fully demonstrated and compared with the conventional DTC means under the PI regulator, and exponential reaching law means the conventional slide mode control, and here ERL DTC is the conventional DTC, and which is compared with the TRL DTC through experiments and validate separately. The experiments have illustrated that the TRL DTC method can get quicker dynamic response. It means it is a faster than the PI control. Stronger robustness under the load and speed change and low thrust chattering in comparison of the both CDTC and ERLDTC. Moreover, here some reduction on the thrust ripple can be further achieved by using TRL DTC, which can decrease the noise and vibration effectively in the whole LIM drive system. So thank you for your attention and for your time. So if anyone have any question, he or she feel free to ask the question.
Yes, audience, if anyone has question, please ask.
Sir, can you hear my voice?
Yes, can.
Yes.
Uh, Sir, I have a question that this sliding mode control using TRLDC has like a quicker response than the conventional. But are there
Yes.
disadvantages like there are some, heating effects in the system or control system because of the quick response of the plugins?
Yes. So actually slide mode control is more faster than the conventional PI control methods. So but it has one disadvantage which is chattering. So chattering is observed with the slide mode control which is inherent problem of slide mode control. But now researchers took a research and they say that by using appropriate slide mode control or reaching law, you can eliminate this chattering phenomena from the slide mode control, just like a super twisting, just like a second order slide mode control.
Sir, one more question that does slide mode has also like the reverse capability? Like if we are going forward and we have like a increasing speed, but can this be used to reverse the induction motors when we have to go backward? Like conventional doesn't go like that. They are just moving
Yeah.
forward.
Yes. I can understand. You are talking about the four quadrant operation. It means whenever machine goes forward and forward braking and reverse braking. So this slide mode control already checked on the different drive system. Just like I personally checked on the PMSM and rotary induction machine. It can work whenever you reverse the speed. Has a same response and same superior response than the PI control. So in this slide or in this talk, I not include that response, but you can check it. It would be the means robust than the PI regulator.
So, sir, does slide mode also have regenerative effects? Like it can be used if we have a higher load. You know about the regenerative, we can create more electricity or have that storage capability by using the regenerative braking. Does slide
Yes.
mode also favors that?
I am talking about the control means control loops. If your controller, if your any hardware or if your any system which contain PI regulator or PI controller or fuzzy regulator or any means neural network, you can replace by using slide mode control. If there is a closed loop, if you are talking about the open loop, in open loop there is no need of any regulator or any controllers. So just you can regulate by regulating some voltage. But if you want to use a feedback control system for feedback, and then you have to compare any quantity, speed or current or voltage, whatever you want to compare, and you use a PI controller. So you can replace this PI control with the slide mode control. The response of the slide mode control is superior than the PI controller. I am pretty sure because I did my PhD and I did lot of work on the slide mode control, and I survey lot of research about the slide mode control in different applications. So I surely pretty sure that this is better than the PI regulator.
Thank you so much, sir.
Oh, thank you.
Sir,
Any
my
other one?
question is that is there any protection system there if any flaw occur during these control system?
Yes, you are right. So I want to show again one block diagram here. For example, this is the slide mode control over here, and this is the PI regulator for the flux and for the thrust. If we use this slide mode control, and we know that our inverter has a capability of, for example, 10 ampere, we not feed more than 10 ampere, so we must place a protection over here, so we must place a limit over here, just like in the response. When I show this thrust response, you can see here, this is the final limit. We took a we put a protection limiter over there. The current not must not goes from this point, so there should be a protection after the means slide mode control.
Yes, any other one having question? Yes, one question from my side.
Yes.
This is just optional. If, for example, if you have any MATLAB environment, any model in MATLAB environment, just to understand what we have studied right now in the
Mhm.
MATLAB environment. If it's possible, then is okay. Otherwise, it's optional. And also, I will ask the audience because Dr. Abdul Khalik Jinejo Saab are expert in sliding mode control, and anyone want to explore more things and want to start research in this area, terminal sliding mode, fast terminal, all different modified sliding mode control techniques. So Abdul Khalik Jinejo Saab are expert in that field. You can contact him. And also the second question, this is first MATLAB environment if it is possible. Then the second question is, uh, how about ripples? I saw the ripples are more in performance in results. And is it possible with this sliding mode control, can we use MPC just for this specific function to reduce the ripples?
Yes, so it would be the hybrid control method. So for the hybrid control method, we can replace, for example, this in this diagram. So there is a space vector pulse with modulation technique, and we use the DTC, direct thrust control method, and one is the field oriented control method. In DTC, one disadvantage is that it is a faster, but it has a higher ripple than the field oriented control method. But this method is a means has a fast response. To replace this DTC, you can use means per MPC, model predictive control over here. When you use model predictive control instead of DTC, you can get better response in terms of the thirst ripple.
Okay, thank you. And
So
also, for example, ripple impacts. How can we see this ripple impact in as on the application of, for example, subway or metro? If the system has more ripples, is there any physical impact on the system or not?
yes, yes, there is a physical impact. For example, when we talk about the chattering in the system, so if there is a higher chattering, you can feel some vibration in the metro. If it is connected with the, for example, host or lift, you can feel some vibration. This is due to the chattering. For the ripple, if there is some ripple, higher ripple in the with the method, so you can feel some for example, this is a Fourier means for example, when you talk about some filters, if there is no any filter, the your system would be heating, your system would be heating if there is a higher ripple in the current.
Okay, thank you very much. And also one question, how practically load can be changed when speed is constant? For example, will be stopped, subway will be stopped, then speed will be zero, not constant. How we can change the load practically?
Yes. And practically, when you talk about any application which is exist in the linear metro, it is not happen. For example, one metro is going and it would be the stop again goes with another speed. For the designing purpose, it is a required that you must check on different speed. For example, it can be used in the electric bike, it can be used for the electric car, it can be used for the train. So sometime you need high speed, sometime you need low speed with the same load, sometime your load is similar, sometime your load is higher. So that's why, So it can be checked on the different scenarios, means some higher speed, some higher load, some lower speed, lower loads, and sometime and rated. When we talk about the rated speed, you should must go up to the rated, then half, then again zero. So these all scenario can be generated. In practical system, what we have done in the lab, we can change this load by changing the anti-clock thrust on the same shaft, or load or torque, you may say torque. We produce anti torque on the same shaft. One motor want to the control it, another motor we produce a torque with it to check the different loads, just like this.
Yes, thank you very much. And any other question from the audience, if I have?
So one thing from my side is that
Yes, please.
if anyone who want to do research or who want to make some thing about the drive system, I am available, and he or she is appreciate welcome to contact with me, and we can make some means some other controllers for the drive system. And also I would try to send a basic model of the slide mode control on PMSM to the Dr. Habib. Then he can share with you how we have to design the slide mode.
Yes, okay, thank you.
Sir,
Okay,
I have one last
yes.
question, sir.
Mm-hmm.
Sir, in slide mode control, as you know that every system has its own precision and accuracy, and as we are talking about metro, its system is autonomous, like it is stopping at every single station, and on exact accuracy, it has to stop. It can't go any way further, or it can't stop before the gates. So, what is the accuracy? Like how we determine the accuracy, and when we push the pedal, like motors has to come to a stop. So, how that precision could be made more better in style control?
Yes. So actually all drive systems work on the some sensors. Some sensors can be used, and whenever one sensor can be used for the speed and for the position. So this should be stop on this. So the precision or accuracy of the slide mode control is more than the PI controller. It means I not say that it is 100%. It can be a 98%, 99%.
Okay, sir. Thank you.
So
So
anyone
you
having
are you are
question?
welcome. Yes, you are welcome.
Okay, let's end this session. Thank you very much, Dr. Abdul Khalid Janeja Sahab, just to join this and for your precious time. And I am hopeful that the next lecture, inshallah, with you about fluctuations due to end effects of linear induction machines, like that, I will try to
Sure.
arrange, and I will be hopeful to join you again, inshallah. Thank you very much
Sure.
again. Thank you.
Thank
Thank you.
you.
Allah
Thank
Hafiz.
you.
Allah
Allah.
Hafiz.